Talk is called distributed trust. I'll explain what that is and explain whether blockchain actually helps with that at all. So everybody knows that centralized means bad, distributed means good, distributed also means blockchain. So what exactly does distributed mean, and what exactly does blockchain mean? So blockchain started as the technology behind Bitcoin. People made money on Bitcoin, and the more hype there was, the more money that got poured in, which made more hype. And startups leveraged the hype to claim that their product has something to do with blockchain, and the money rolls in. So after hearing so much of this hype, it's natural to assume that blockchain, whatever that is, must be important. So because I'm sort of known as the blockchain skeptic, at my company, people keep sending me all these articles to amuse or annoy me. So there's all sorts of articles about how blockchain is the biggest advancement in technology since, like, for instance, the internet, or being considered for all sorts of problems. Now, I wouldn't think that would be news, that it's being considered for all sorts of problems rather than being, actually used for. And my favorite was even the US military is looking at blockchain technology to secure nuclear weapons. So the claim, there's another claim that governments can't outlaw cryptocurrency. And yes, they can. And maybe they'll catch you if they find the software for using it on your computer or something. So maybe if you're careful, you won't get caught. Just like with murder, you sometimes get away with that, but that doesn't mean that the government can't outlaw it. So what exactly is blockchain? There's so many variants of it these days that it's hard to separate a blockchain technology from a non-blockchain technology. So I'm going to do a quick introduction of it and focus on the distributed trust aspect of it. So people hear that blockchain is immutable, distributed, it involves ledgers, and it requires massive amounts of computation. So what do these things mean? Well, it started as a paper in 2008 by a pseudonym, Bitcoin, a peer-to-peer electronic cash system. So the design powering this was called blockchain. So the design goals of this was don't trust any known organizations like banks and governments, and you want to prevent governments from doing things like shutting the system down, making you pay taxes, being able to follow a money trail, preventing you from transferring money to terrorist organizations or collecting ransom money. Now, whether or not those are good goals, it does lead to an interesting design, but there's a lot of misinformation about its characteristics. And we'll explore what, if anything, this thing provides that couldn't have been done before. So to save time, I'm going to simplify the details and, again, focus on the choices that impact trust. So what is blockchain? A bunch of anonymous nodes. Anyone can be a miner or a ledger maintainer. So no one knows how many of them are or who they are, and they collaborate to create a ledger. Now, a ledger is just an append-only log. So most systems, every file system has an audit log that records significant events, like who modified the file last. In blockchain, the ledger is kept forever in its entirety. In traditional logs, it's usually okay to discard older information. In Bitcoin, the items on the ledger are items like public key A is sending some amount of Bitcoin to public key B, and public key A signs this transaction. So the format of the blockchain is that each block has a hash of the previous block, a random number called a nonce, the miner's public key who managed to put this block on the blockchain, and a bunch of transactions. So this hash is what's called pre-image resistant, meaning that it's designed so that it's infeasible to find any other data that has the same hash, which means that if you wanted to modify this block, you'd have to modify everything afterwards as well. So what's not new is the concept of keeping a log or having data structured as a linked list of blocks. There's a much more general data structure known as Merkle trees, which are older than the concept of blockchain, and they're much more general. A blockchain is just a Merkle tree with no branching. So what is new? The idea of having an integrity check without any authorized entities and the ability to dynamically adjust the difficulty of finding the next block. So we'll explain what that means. So ledger maintainers, if you're lucky enough to find a valid next block, you're rewarded with some Bitcoins. So you build on the longest valid chain you've seen. Now, a valid chain, you have to verify that all of the transactions in the chain are valid. So to create a new block, you take a bunch of valid transactions that have not yet been recorded and you throw in a random number and you compute the hash. The hash has to have a certain number of leading zeros or be smaller than some value. So if the hash is too big, which it almost certainly will be, because the hash has to be very, very small, you change the random number and try again. So the size of the hash is adjusted periodically so that on average, a new block is found by the mining community about every 10 minutes. So if blocks are being added to too often, then you make it harder by making the maximum hash value be smaller. And if it's too long between blocks, then you make it easier. So currently the hash needs to have 71 leading zeros. 2 to the 71 is a very large number, and that's how many hashes the Bitcoin mining community computes on average every 10 minutes. And that's why it uses up so much power. So the security of this thing depends on the blockchain community having an insurmountable amount of computing power. If some nation state had more compute power than the blockchain community, they could create a longer chain and erase part of the chain. And I'll talk about forks later. And by replacing the last n blocks with a longer chain, n+2, because you had more compute power, you can get rid of some transactions and you could respend the money. Now, with traditional cryptography, the way that you make it hard to create a fraudulent data is that authorized entities have public keys and they know a secret, which is the corresponding private key. And the magic of cryptography makes there be a huge gap between the compute necessary to create a signature versus forge a signature. So for example, with 2000-bit RSA, the amount of compute necessary to sign, if you know the private key, is about 6 milliseconds on a typical CPU. But to forge it would require the entire compute power of the Bitcoin mining community for the next million years. So that's what I mean by a big gap between an authorized signature versus trying to sign it. Whereas in contrast, blockchain is equally expensive to compute as to forge. So now I'll talk about centralized versus distributed. So is centralized bad? Centralized means one organization is in charge. Usually centralized means also that there's lots of servers, so the application is always up, even though they're all sort of owned by the same organization. And usually it means that your data is stored in multiple places, geo-replicated, especially if you're using a public cloud, they will do that for you. So if a data center burns down, your data is still there. Centralized is the most efficient, and it's clear who to blame. So if it's a big company and they start doing bad things, you can sue them. But if it's just kind of a bunch of anonymous entities, and also most applications require adult supervision. So for instance, if you're using eBay and you send money and the merchant doesn't ship it, you complain to eBay and they'll sort it out, they'll get your money back or something. But if you use Bitcoin and I don't know, what would you buy with Bitcoin? I guess a hitman or something. So if you hire a hitman and you pay him the money and he doesn't kill who he's supposed to kill, who do you complain to get your money back? So most of the time, centralized is exactly what you want. And for instance, if you withdraw $20 from an ATM machine, your own bank makes a decision about how much money you have in your account and whether they should give you $20. There isn't a consortium of banks that vote about it. So distributed trust, any organization can become evil, either because they hire an evil employee or somebody steals their private key and impersonates them. A Byzantine failure means failing not by just halting, but by misbehaving, doing the wrong stuff. So how do you make a system that's robust, even if some of the participants are misbehaving? So there's lots of approaches. There isn't a single solution to making things robust. And being robust, despite having malicious participants, is not equivalent to the Byzantine agreement problem that there's been so many academic papers about. So I'll show some examples to show how there's many different types of problems and approaches. So one really simple case is if you have multiple independent sensors, like on an airplane, and you want to see how high you are in the sky, you might have 3 independent sensors that don't speak to each other. They independently get their own data, and the answer is read from all 3. And you assume if 2 of them agree that must be the right answer. So one of them can be flaky and it won't affect things. And I don't see how blockchain would help with this problem. Credit rating agencies. Currently, the way that it's done is anyone who wants to be a credit rating agency can just declare themselves to be a credit rating agency. And perhaps you might have third-party accreditation agencies. So the credit rating agency can get certification from Good Housekeeping and whatever. And you can get as many certifications as you want to say, yes, this organization says you're good, this organization says you're good. Each of these credit rating agencies operates completely independently with their own sources of data and their own algorithms for computing a score. Someone who wants to check your credit rating can ask whichever of these things they trust, or they can ask several. And then there's also laws that allow consumers to contest data that they think is wrong. So this seems rock solid, and doing a blockchain solution where you'd have some consortium and who gets to be in the consortium, and they have to consult with each other, it seems far less resilient, certainly less efficient, and less secure. So part of a distributed system that people don't think about is a human. So this is an example of web security. So the theory is so beautiful. The website has a name, a DNS name, x.com, and it has some sort of certificate. And the client says to it, are you really x.com? Prove it to me. And the x.com sends a certificate, and there's all sorts of cool crypto. And then they have a cryptographically protected conversation. But in reality, usually a user doesn't start out with a DNS name. And instead they do a search and get some sort of obscure URL string. That's an actual URL string. Even if the user can look at that URL string and find the DNS name in the URL, I actually fell for a scam recently. I wanted to renew my Washington State driver's license, and I knew it could be done online. So I did an internet search for renew Washington State driver's license. I clicked on the top listed site, and I do understand all the underlying protocols in crypto, but it didn't occur to me that the top search wouldn't be correct because I was tired and in a hurry. So this is the top search that I got. The URL looks reasonable, washingtoninformation.org, driver's license renewal. I didn't notice that it said add, but often the top things that you're searching for say add anyway. So everything was as I expected once I clicked on it. There were all these little pictures of happy people where you could say, I want a new driver's license, or I want to replace my license. So I clicked on renew driver's license, and it asked me all the things I expected. It asked me for my address, my driver's license number, and my credit card. And so everything was great. And then they charged me $3.99 the first day, then $9.99 the next day, then $19.99 the next day, at which point the bank fraud department called me and asked me if these were legitimate charges. And I said, oh, let me explain what happened. And they said, oh, sure. And so they disallowed all of the charges and gave me a new credit card number. So I was not injured at all. And it gives me an actually a great example. So I'm really pleased this happened. So one thing I want to challenge the industry is don't blame the user. These scam sites appear first, either because they pay the search engine companies or because they understand the ranking algorithm and game the system. And this particular scam at the time I fell for it had several names for all 50 states. So it was idahoinformation.org and whatever. I think that they've now shut down that scam, but I'm sure this scam will happen all the time. And the site I should have gone to was this. Why should I, as a human, remember that DNS name? So this is a quote from my book, and I wish everybody would kind of memorize it and take it to heart. Humans are incapable of securely storing high-quality cryptographic keys, and they have unacceptable speed and accuracy when performing cryptographic operations. They're also large, expensive to maintain, difficult to manage, and they pollute the environment. It is astonishing that these devices continue to be manufactured and deployed, but they are sufficiently pervasive that we must design our systems around their limitations. So, how many participants can be faulty in a reliable system? So everybody knows that to be robust, despite malicious participants, a majority of the participants must be honest, or maybe it's 2/3. So let's look at some example systems. So reputation systems, thousands of anonymous participants is always problematic. You have no idea what the total number is. A bad guy can create zillions of identities. So for instance, when you look at online shopping reviews, which I do when I try to buy something, you don't know whether the rave reviews are all friends of the merchant or whether the bad ones are friends of a competitor of the merchant. So network routing. This was actually my thesis. And if you want to find it online, you look for the title, Network Layer Protocols with Byzantine Robustness. So the goal was 2 nodes, A and B, should be able to communicate across a network with a fair share of bandwidth, even if some of the switches are malicious, as long as one honest path connects them. So what can a malicious switch do? It could give false information in the distributed routing algorithm that the routers use in order to calculate forwarding tables, or it could flood the network with garbage data. It could forward packets off in random directions, resetting the hop counts to make packets look new, or it could do everything perfectly, but throw away traffic from a particular source. So, it's working well for everybody except one guy. So when I proposed this as a thesis topic, everyone said, oh yeah, that's important and difficult. Then when I actually did it, I've never done anything complicated. It was like embarrassingly simple. And I was afraid they wouldn't give me a thesis for it, but they did. So flooding, I realized if flooding is where you just transmit each packet you receive to each neighbor except the one from which it was received, and you have a hop count so packets don't loop infinitely. And hey, that works. Packets between A and B will flow if there's at least one non-faulty path. But that requires infinite bandwidth. So yeah. So now it's just a resource allocation problem. So the finite resources are computation and switches. And you could wave your hand away and say, we can just assume that we can engineer router boxes to keep up with wire speeds, and we can. The other two are memory in the switches and bandwidth in the links. So for memory, each router or switch, I use them interchangeably, each switch reserves a buffer for each possible source. And for bandwidth on each link, each switch round robins through the buffers so that every source's packet gets a chance to go. But you have to make the source sign the packet, or else somebody else could claim to be the source and occupy the source's buffer. And you also need a sequence number so that somebody can't inject old packets from that source, starving out the new packets. So configuration, every node needs to know every other node's public key, and that would be kind of a lot of configuration. So instead you have a trusted node, which will be similar to a CA, where it knows the public keys of all the other nodes, and all the other nodes need to, if you bring a new node into the network, it has to know its own private key and what the trusted node's public key is. And since everybody knows the trusted node's public key, it can flood. And the information that it floods is, here's the public keys of everybody else. So you might say, well, isn't the trusted node a single point of failure? Well, it can't subtly fail. If it advertises the wrong public key, or it doesn't advertise your public key, you can immediately report it and it would be fixed. But also, if you really care, you could have 3 public nodes and only believe public keys that are advertised by 2 of them. Or even if you just have 2 of them, you could reserve buffers for each advertised key. So a bad trusted node can at most waste half the resources, but it would also get caught really quickly. So it's inefficient to actually send data with flooding. So we're going to do something else for unicast, which is where a source wants to send a packet to a specific other node. But we're going to use the robust flooding for 2 things. One is making it easy to do configuration because the public keys will be advertised. And the other is for distributing link state information. So what is link state information? Here's a network. There's 7 nodes, and F and G are neighbors with a cost of 1. So that's what that picture means. And this database, each of these switches is responsible for generating a packet that I call a link state packet that says, I am A, I have a neighbor B at a cost of 6 and D at a cost of 2. And these packets get flooded using the reliable flooding to all the other routers. So all the switches have this identical database, which is enough information to draw a picture of the network and calculate paths between any pair of nodes. So with traditional forwarding, each switch along the path makes the decision for which next hop to use. And I decided that wouldn't work for, including sort of malicious switches in there. So a bad guy, if you did that, could keep the network from never converging by constantly flipping the state of a link. Or what do you do if there's a path that works for everyone except a single source? So the conclusion is that the source has to be able to choose its own path. So for data packets, the source uses the link state database to choose a path, sets it up with a cryptographically signed packet specifying the path it wants to use, and the routers along the path have to keep per SD pair the input port, the output port, and the buffers for any data packets that will be forwarded on this flow. So S will send a packet that says, I want to get to D by going through R3, R7, and R2, and that will go along this path and cause R7 to say, when there's a packet from S to D, I should expect it to come in on this port, and I should forward it on that port. So for unicast forwarding, there's no cryptography needed on actual data packets. You don't need like signatures or anything. All you need is an additional check saying, is this data packet coming from the input port I would expect it to come from? And as long as the path is honest, no malicious switch off the path can disrupt the flow. So forwarding is as efficient as for traditional networking. And how can S choose a path that works if there's a bunch of malicious guys out there? Well, if a path to D works, which you'll know because of end-to-end acknowledgements, then you'll trust the routers that were along that path. And if the path doesn't work, be suspicious of the routers on that path, but you don't exactly know which one was causing a problem. You could try to eliminate routers one at a time, but if there's lots of bad guys, it can be really expensive. So it was good enough to get the 3 signatures for the thesis, but certainly there's other things one could think about along those lines. So the summary of the design, the source has the fate in its own hands. So there's no need for agreement. So this seems like it should be harder than a Byzantine agreement thing where a bunch of nodes have to agree on the value of a single bit. But it's actually much simpler because there's no need for having anyone agree. And a huge majority of the switches can be malicious. As long as one honest path exists, A and B can communicate. So a contrasting example is there's this fascinating paper called How a Lone Hacker Shredded the Myth of Crowdsourcing, which you can just search on the internet, or here's the URL of it. Crowdsourcing seemed like a promising approach to solving hard problems where you just advertise, we want to solve this. Anyone who wants to participate can help with the group solve the problem. But a single bad participant among thousands of participants made the whole effort fail. And so you should read the paper, but it's kind of fascinating also how the journalist tracked down who it was that was actually disrupting this and his reasons for doing it. But the conclusion is having a majority or 2/3 of honest participants is neither necessary nor sufficient. So more examples, storing data robustly. You need to store it in multiple places, geographically diverse in case the data center burns down. But a malicious cloud could modify your data. A cloud administrator with root privileges can modify your data or delete all copies. So to detect modification, you could sign your data, but if somebody stole your private key, they could modify your data and sign it again with your stolen key. So even having your own signature on it, you can't completely trust. So you should get multiple independent entities to also sign it. So yeah. But that just tells you, your data is messed up. It doesn't actually help you get your data. And no matter how many copies there are, someone can delete all the copies. So I really miss mag tapes back in the days where if you made a backup and you stored it in Iron Mountain, nothing could hurt your data. So to be robust, in addition to integrity checks, you need to store the data in multiple independent clouds. So with public blockchain, the ledger gets stored in tens of thousands of places by whatever anonymous entities feel like participating. So that sounds like, wow, that's incredibly robust. You'll never lose data. But with a public cloud, they keep typically like 6 copies. The cloud is contractually obligated to keep n copies. But with a public blockchain, no matter how many copies you have, nobody is contractually obligated to hold on to it. So some of these blockchains have completely gone away, and any data stored on it, there's no copies of it. So what is the sweet spot for how many copies of data should be? I presume that it's closer to having 6 copies rather than 30,000 copies, especially 6 copies stored by some professional organization that keeps track of if one of them has gone down, it'll spawn up another copy. But I work for a storage company, so sure, why not store it in 30,000 places? Now, another problem is proving that something happened at some point. So the way I would do that is you have this thing called a notary. That's a very simple thing. It knows its own private key. And if somebody sends it a hash, it just mindlessly puts the time on it, signs it, and sends it back to you. The notary can be extremely lightweight. It doesn't have to even keep the data that it's notarized. It just sends it to whoever wanted something notarized. And then you'd say, well, what if the notary is dishonest so someone can bribe it to put in an old timestamp? Or if the notary goes out of business, well, just get it timestamped by several notaries. You could get it timestamped by hundreds of notaries. It's so incredibly low overhead and resilient. So proving when something happened is a plausible use of blockchain that people sometimes say. So what you can do is you can add a hash of something, like a hash of a document describing that you've invented something to the blockchain. And then you can prove that the document existed at that point because the hash that you put in is in a particular block, and the blocks are timestamped. And if the blockchain truly can't be forged because it's prohibitively expensive, as in Bitcoin, this would work, but it would be expensive if everyone used it for lots of things because the ledger would get really big. And to me, notaries seem just as secure and way more efficient. And with a private blockchain, where there's only a few in the consortium, it might be easy to bribe enough participants to insert your hash earlier in the chain. And so again, even with a private blockchain, notary solution seems way more efficient and secure, especially if you use lots of reputable notaries. So how resilient is blockchain really to Byzantine failures? So one issue is communication. The internet doesn't have a mechanism for addressing a packet to say, send this to all the Bitcoin miners. So instead, you need to configure all the miners to have links to several other miners, where a link is just configuring them with the IP address of other miners. With lots of redundancy, this would multiply the number of messages. And without lots of redundancy, a few miners going down can cause partitions. So here's an example of a network. And if this node went down, the network would be partitioned. And nobody knows how many miners there are. So there's no way to tell if the network is partitioned. So at this point, that partition and this partition would happily be adding onto their own blockchains, and you would have two separate chains that forked at the point where the partition happened. So what forks are is this is a valid chain, and this is also a valid chain. But since everybody will try to build onto the longer chain, once the guys over here see the longer chain, they will completely forget about these blocks. So any transactions that were in the losing chain, or any Bitcoins that got mined by being in, by finding these blocks, they no longer exist. So what causes a fork? Well, an attacker that has more compute power can introduce a longer chain or a network partition, or because of variable message delays, it's possible for multiple miners to simultaneously find a valid next block that has a small enough hash. So Bitcoin says, well, the rule of thumb is you should wait to make sure that your item will be in the ledger, wait to see it in a block and see 6 extra blocks before you can feel safe that your transaction will stay. But that's like an hour. So if you're paying for your coffee with Bitcoin, should the coffee shop make you wait there for an hour to make sure that your transaction of paying them will actually stick in the ledger? But there's actually no amount of time that guarantees your transaction will stay. Another thing that happened was there were 2 different implementations, and there was a transaction that looked valid to one implementation and looked invalid to the other. So all the implementation that thought the transaction looked invalid ignored that block and anything beyond it. And so it wound up with 2 different chains, because it was actually the old version thought that that was an incorrect transaction. So they just happily built their own chain, ignoring anything past the block with the invalid transaction, and the newer nodes happily built on the other one. Also disagreements about changes. So some people in the Bitcoin community wanted to change the block size so there could be more transactions per unit time, but not everybody agreed. So that caused a permanent fork into 2 different currencies, one called Bitcoin and the other one called Bitcoin Cash. So another thing, people say that the ledger is immutable. And the only reason that you can't just sort of create a different ledger that looks valid is that it assumes that the blockchain mining community has cornered this, the market on compute, and that no nation state could possibly put together an alternative chain. Now, the Bitcoin's mining community does have an awesome amount of compute power. It's estimated that it's currently using 7.7 gigawatts in order to do all these hashes. And to put in contrast, the largest US nuclear power plant generates 4 gigawatts. So that's how much energy the world is using on this very low volume thing that's mostly used for collecting ransoms for ransomware. So it might be really hard to create an alternative Bitcoin ledger because of how much compute they have. But there are zillions of other cryptocurrencies being created, and most of them do not have all that much compute power. So it is easy to put together enough compute to change those ledgers. So when you're using Bitcoin, if somebody pays you in Bitcoin, you'll get a message that says some public key pays your public key what they received in some previous transaction that had hash H1. So will you be paid? You have to find somewhere in the ledger a transaction with hash H1. P has to have been the recipient of that transaction. You have to search the entire ledger after H1 to make sure P hasn't already paid that to somebody else. Then you have to make sure that the transaction is solidly in the ledger, or else P could pay it to somebody else. So this is expensive, especially keeping the entire ledger. So in general, people using Bitcoin don't do this. Instead, they ask, their implementation is configured with the IP address of some full node, and they just ask that node, should I trust this transaction? And it answers yes or no, and you trust it. So you're putting all your faith in one thing. Now, in theory, the client could ask lots of full nodes, but I don't think implementations tend to do that. And same with a permissioned blockchain, where you have a consortium of organizations, a few, and they collaborate on creating a ledger. But the API where a client talks to them, it isn't like they ever show them the ledger. The client says, would you store this thing for me? Or it says, is this thing in the ledger? And the client will completely believe what N2 says. Now, in theory, the client could ask a majority of these nodes, but again, I'm not sure whether they do. So in a public blockchain, what can a malicious ledger maintainer do? It cannot put an invalid transaction onto the blockchain because nobody else would believe this block. And that block will soon be superseded by a longer chain. Or maybe it would cause a fork if some people believe that transaction or don't check and others do. However, a malicious one can discriminate against some transactions. It can delay forwarding a transaction, or it could just not include them in a block, and nothing prevents this. And full nodes can lie to clients. So when people say that blockchain has Byzantine robustness, I really don't know what they mean by that. So what are the security properties of private blockchains? If you have a consortium of K independent organizations, presumably there'll be some sort of quorum scheme among the ledger maintainers. So you would need to subvert a quorum of them to overwrite history. But if queries are to one node, then that node can lie. And if write is to one node, it can ignore it and not write your transactions. Or if you have something which is like blockchain as a service, where all of the nodes are run by a single organization, even if it put in signatures rather than just hashes, even with signatures, that one organization can completely create a new ledger, and you'd never know the difference. So what are the positive security properties of it? It's basically just an inconveniently formatted database. So the only positive thing I can think about that is that it allows you to say you're using blockchain and seem trendy. So possible questions people ask is, what kind of applications can I build on blockchain, or how can I apply blockchain to this problem? And I say, no, that's the wrong question. Instead, you should start with, what problem am I solving? Look at various ways of solving it, compare approaches, and if blockchain turns out to be the best solution, then okay. So more examples. There was a direct quote from a blockchain article somebody sent me. Could blockchain be the answer to healthcare? Imagine this, your entire medical record is on the blockchain. Monitoring systems and IoT devices automatically update your data. So when you go for diagnostic tests, the results are recorded without a third party. I can't imagine an application less suitable for blockchain. A world-readable database, a world-writable database. Who is going to assign credentials so you know that data that's being written is actually written by a valid censor? No organization to the data other than an append-only log mixing together every human's records and censor readings. No way to correct errors. Data kept forever in its entirety. So yeah, I'm sure someone will think of using encryption to get around the world readable issue, but with what keys do you encrypt it, and how do you get the keys? Do you have trusted third parties? If so, then why not have them manage the database? So the last example I'll talk about is supply chain, which is a common keynote talk at blockchain things. I'm saying that there's this important societal problem of children dying of E. coli poisoning. And the solution is record the supply chain on blockchain. But they could also way more efficiently use any sort of storage system, any sort of database. And it doesn't answer any of the hard problems. Who's going to give credentials to the farmers so you know that what's being written is correct? Who's going to put RFID tags on lettuce leaves so that if you get lettuce from multiple sources, you know which lettuce came from where? And a database would be so much more efficient. Also, do we really need to keep an entirety? Who grew lettuce 5 years ago? And what if the database maintainer is dishonest is an obvious question, and then use several independent databases. So in summary, start with what problem am I solving, consider several types of solutions and compare them, and don't say, can we use this technology for this application? So sometimes engineers come to me and they say, oh, but my manager really wants us to use blockchain. And I say, fine, do what I'm saying, figure out what the right solution is, build that, and then tell your manager you're using blockchain and he'll never know the difference. So thank you.
So we have a Slack channel, ATC OSDI 0714 Keynote, in which you can ask questions of Radia. And I guess while we're starting out, if any of the chairs would have questions about the keynote before things come up in the Slack channel, you're welcome to ask questions.
Yeah, I have a quick question. So you mentioned a few applications where blockchain might not be the best solution for, but you said if blockchain is the solution for your problem, then use blockchain. Can you give us some examples of some of places where we do want to use blockchain?
I really don't, I'm not a fan of it. So I really think that having multiple different organizations in competition with each other, doing business, by themselves is really, the right solution for everything, except for possibly having a currency that, enables ransomware. That seems to be the killer app for the public blockchain. So yeah, I really do not have a good example.
So I have a story related to that. I guess while we're waiting for more questions, back in 2005, there was this program called a time capsule. So Forbes wanted to create time capsules for email, so you could send yourself an email that you would get 20 years from now. And there was a question of what do you do with these emails? Who's going to store them and make sure that the system still functions 20 years from now, right? And I really like the point about the human being kind of the weak link in our systems, because what happened is they chose 3 organizations and they said these 3 different organizations will store the emails for 20 years. And they actually had checkpoints. So they would send an email 1 year into the program, 5 years into the program, and then 10 years and the 20 years. So this was in 2005 and the 20 years didn't happen yet, right? So we'll see if they survived this long to send the emails. But what was interesting was that 1 year into the program, one of the organizations was Yahoo. And 1 year into the program, everybody who was involved, all the humans who were involved, had left Yahoo or they had been laid off. So nobody really wanted to continue the program on the Yahoo side. So I guess only 1 year into this, they were left with only 2 organizations being part of the program. So I'm curious, like, what do you think of how many organizations do we need to involve? And how do we keep the humans interested in continuing the programs? Because we have to continuously update and make sure that the system is still working, right?
Right. So, you know, that's sort of a great different way of expressing that if you store your data in all of these anonymous miners versus giving it to a professional and paying them to keep your data, and they only keep 6 copies, whereas you have 30,000 miners, it's actually more reliable to have some sort of live system that is professionally run.
So we have a
always use multiple independent clouds and check on it periodically.
So we have a couple of questions that have shown up in Slack. Denise Altenbicken asks, why do you think blockchain became a quote solution for all?
Just because of all of the hype. So the combination of people seeing that people were getting rich on it, that made a lot of news buzz, and then a lot of startups that were saying, oh, we're doing things based on blockchain. Definitely, I run into a lot of engineers that think that that is one of the most important technologies ever. So there was some organization that was doing a whole blockchain thing. And after I gave a talk, a skeptical talk, the guy who was head of it said, I want you to look at our technology. So he was showing me all the stuff they were doing. And I said, gee, that's actually good stuff. But why are you calling it blockchain? Because it really doesn't look like blockchain to me. And he said, for marketing reasons. So, you know, definitely just because something is called blockchain doesn't mean that it's bad.
Riz Zadok has a multi-question. He says, it seems odd to me that end nodes have to keep all the chain info indefinitely. Does that scale? What's the size of the total amount of data that has to be kept by each node? How quickly does it grow? Would it fit in RAM? If not, at which point it becomes IO bound and everything slows down even more?
Right. So it's also very expensive in terms of network bandwidth. There are usually people who want to pay with Bitcoin with their smartphone. They wouldn't keep the ledger. They would just go ask us a full node, and it's only the full nodes that keep the entire ledger. Now, there's ways you could compress the ledger. You know, perhaps you could have less full nodes or something that get rid of all of the transactions that have already been spent because you don't need to look at them again or something. I don't know. I don't think that they do it yet. I think that the ledger is currently like 1/4 of a terabyte. So it's not, well, okay, I don't know whether it's big or small. I guess you think that's big. Again, I'm a storage company, so the more places, the better. The bigger the ledger is, the better. And it's only a very low volume thing. You know, like they keep talking about anyone who wants to prove that they have something, you just stick that hash on the ledger, you know, or all of the information about every head of lettuce that has been grown or every sensor reading, put all of that on the blockchain. Yeah, it's kind of overwhelming.
Well, I will note that the standard configuration of an Apple laptop is 1/2 terabyte. So if the blockchain is 1/4 terabyte, then that's taking up totally half of your disk space just for the blockchain ledger.
Well, surely nobody has any data they'd want to store that's any more interesting than the blockchain, right?
So I have a sort of related question. Is there is there any hope? I guess, is the computational cost of blockchain inherent in the concept? Is there any hope of being able to, if we have a technology, say I do want to hire a hitman, do we have any technology that would allow me to hire the hitman without using up the total power output of a small country?
Right. Well, certainly there is cryptocurrency, like we use wire transfers and credit cards and stuff like that. So certainly we can do things electronically, and it doesn't have to involve, any sort of expensive thing. China had a really cute scheme called digital cash, and it involved a single bank that would issue currency, but do it with what's called blind signatures. So the bank would not know which money was attributed to which people. So it was quite anonymous, actually even more anonymous than than blockchain, where the blockchain information is publicly readable, and lots of data is mined off of there, where they really can figure out, what it's being spent for. There's also like M-Pesa is something done in a whole bunch of countries where it's the cell phone company that's like acting as the bank, and it keeps track of how much money each one involves. Now, in terms of the public blockchain, there are alternative things being presented all the time. So there's this proof of stake business, which I can impersonate someone who understands it, but I don't really, where whoever has the most money can sort of bet in terms of whoever has more money is most likely to build the next block. And if they misbehave, they'll lose their money, but I don't know who decides who misbehaves and stuff. So that's one thing that's gotten a lot of press, at least, but I'm skeptical of it. Another thing that was recently done, which I recently published, which I think is sort of cute, is a time-space trade-off. So their thing is called Chia, C-H-I-A, like the pet that grows hair. And they liken it to farming. And the high-level idea is that you pre-compute a bunch of hashes, and so the more room you have to store these things, then when the next block comes up, you don't know beforehand what kind of thing to expect, and whoever has like the hash that's closest to what's needed for the next block can put the block on. So it's a traditional time-space trade-off. But the whole thing is, yes, we might be able to come up with better ways of doing this public blockchain, but why on earth do we think that's a necessary or the best solution to things, is at least what I want people to pause and ask about.
Okay, I think we're out of questions, and we're actually right on time, which is good. So thank you very much, Radia, for a really great talk, and for confirming my belief that I can probably eat my lettuce safely without using up a nuclear power plant.